TR 4101, 5101. This is lecture number 10, and today is going to be a shortened lecture because we've already done quite a bit of demo already, and we're going to cover pretty much all of Chapter 4. One thing to keep in mind is with Chapter 4, we go through several skills of which have been demonstrated already. So right before Lab 1, Mike McLean went through the demonstration of the tools, how to use an integrated development environment. And just a few minutes ago, we did a demonstration of the debugger. And so what I will go over in this class will be some of the theoretical underpinnings of integrated development environments and some more on software. So this class, the rest of the class will cover all of Chapter 4. And so I would like you to make sure that you read up Chapter 6 for the next lecture. So let's step back and say, and as I usually cover for class, I'm going to cover the application, embedded application of the day. And it is, what in the heck is that? For those of you who have already talked about it with me, don't say, but what do you think that is? Should I zoom in? All right, that's obviously a speaker. Good. What do you think that looks like? By the way, to give you an idea of how big things are compared to everything else, that's a big paper clip, not a little one, all right? So what do you think that is?
Mic.
Okay, it's actually a battery. It's one of those small pill batteries, but it's actually pretty big, right? So you put it next to my finger. It's a pretty big battery. All right, battery speaker. What does that mean? What? Obviously, something is playing, right? It's either going to be voice or music. Here's the further answer. All right. So, what do you think that means? All right. So this is a greeting card that plays music when you open it. All right. So if we look on this. All right, so yeah, I could play that again and again. Here, let me bring it close to the what do you call this? The camera. And here we go. All right, they get the idea. So. Think about this. This is a greeting card. Does this say how much it costs? No, didn't put it in here. I think it was $4. And this is the ultimate consumer electronic. Think about this. If we look very carefully what's here, extremely inexpensive speaker, extremely inexpensive battery, and then let's just dig into the printed circuit board. Yeah. Okay, that's enough. Right, here we go. Here's our printed circuit board, and it's actually fairly simple. They do have some silk screening, so you can kind of tell what it is. And as we mentioned before, what does the designation R1 mean? Resistor. C1. Capacitor. Do you see any capacitor there, by the way?
Nope.
No.
Top right.
Yeah. C1.
There's C1, but there's no cap.
There's nothing there. So here's the question. You think it's on the other side, right? Or is there? Yeah, it doesn't look like there's anything on the other side. So So the whole idea is that they want to make this as cheap as possible. To make it cheap, do you think you actually do something like put parts on two sides? No, that means you need to process both sides of the board. So you don't want to put anything on both sides. You want to solder on one side. Hence you see they're soldering here, and that's soldered there. And what is this big thing right here? See if I can get any better. I could probably hit auto focus. Now the designation U stands for what?
IC.
Some sort of IC. So it says U1, but there's this big blob of epoxy there. So what's underneath there? It is an IC that hasn't been packaged in a piece of plastic like you used to, right? They took the dye, the silicon dye, and they put it on the board, and then they took little wire bonds off to the side, and the wire bonds are connected to these connections going in. You know what? I should probably turn off the lights. That would make it easier to see, wouldn't it? Or would it? Yeah, it doesn't work. And I'm afraid if I turn off the lights, you'll all go to sleep. So, underneath there is a microprocessor. Because how could this thing play audio without having a microprocessor? It's not like a little record player, right? There's not a little needle and oh, that's right. You guys don't know what old vinyl records are like, right? So there's a small microprocessor in there. And think about this. Do you think they're programming the microprocessor, or did they manufacture the processor with all the data on it and all the code on it? All right, so they manufactured it with all the data and all the code on it because how many of these things are they making? Perhaps 1 million. I mean, how many people want to buy a card that has Johnny Cash singing? I don't know. A couple of you up there. Yeah, there you go. So you probably made at least 100,000 of these, which they're shipping all over the U.S. and Canada and some other countries that might buy it. You never know. And in that same vein, I thought, well, if I look at this, there's a couple of pins here that look like. What if I shorted out that resistor? I'm thinking that says 224. So that's the size of the resistor. 22 times 10 to the fourth. Or I think it's 2.2 times 10 to the fourth. And I'm thinking, I wonder if this is smart enough, the microprocessor is smart enough in there to know that if you put a different type of resistor in there, maybe that plays a different song. Wouldn't that make sense? You manufacture one chip that has different songs in it, and depending on the value of that resistor that you do all the way at the end, it'll play the chicken dance. I had one that played the chicken dance. Everybody know what that is? I tell you, for the foreign students who aren't familiar with the chicken dance, maybe I will find the chicken dance card and play that. And you know that.
Yeah, the Irish cricketers do it when they win.
They made you do it where?
The Irish cricketers from Ireland, they dance. So when they get a wicket or something, when they have a score in a cricket, they do that. So
that's one of the more annoying things you can have, but they played at all the weddings here, so what the heck. So I was thinking, so if I change this as I play, you get that?
Yeah, that's great.
So for some reason, it just speeds it up. So I guess I was wrong in that. But at least it does something different. Again, this is an example of extremely cheap embedded system Because if this card is costing $4, they have to manufacture the whole thing for less than $1, including how much it costs to get a license for this song. Because, you know, they have to pay now for every one of these things that's sold. At least it's not for every time it's played. But for every one of these sold, they have to play or pay some money to Johnny and June Cash's, whoever owns the copyright of that song. So, if you're into the world of embedded systems, this is a good example of an extremely cheap commercial device. All right, so let's go on. Let's see. So embedded of the day. Oops. Man, all right. So my arm scares you, does it? It scares me so much. So I'll just keep that up there so we're able to look at it a little bit later. So, what I would like to discuss is associated with Chapter 4 is software development. So you already know how to use the Integrated Development Environment, IDE. We've shown you how to do debugging. And oh, by the way, you already know how to do simple use of tools. And the nice thing about that is think about this. How many of you have taken one of, or you're in Dr. Sass's C course, right? And he does everything at the command line, right? So you basically write raw code using some sort of text editor, which tells you nothing about the structure of that code, and then you type on some lines, GCC or something else like that, right? To compile your code, and then you take that code and you do something else with it, right? So what have we done? We have created for you a beautiful IDE, Integrated Development Environment. Which is a whole bunch of tools in one package. So what is this tool? What are all the tools associated with this? What's in there? A compiler. What else?
Linker.
Speak up.
Linker.
I can't hear you still.
Linker.
A linker.
Debugger.
A what?
Debugger.
A debugger. What else?
A flasher.
A downloader, I'll call it, right? What else? Probably one of the main ones you've probably used it for already, right? Text editor, right? And I'll even go a little bit further, and I'll call it a project creator. So you're creating a project. In other words, it's doing a lot of the easy work for you, or it's doing a lot of the work to make things easy for you to use this entire development environment. Now, how many of you have used an IDE like this before for embedded? All right. How many of you have used something like this when you're talking about like writing your C# programs, C, C++? So some of you as well. All right. Think about all the things that have to be done or that you have to know about. So if you are developing an embedded system and writing code, I got to put this up here. you know, what you need to know about your embedded system, right? In particular, your hardware. So does anybody have their board with them? I can just hold up? Nope, that's all right. Nope. So if you look at your board, what's important to know about this board? That might be right there in the middle of the board.
Type of microchip.
All right? You need to know which microcontroller are you using? Why is that important? What's on a microcontroller, at least that we know about so far? What's important? What's on it?
Instructions. Instruction set.
All right, the instruction set. Who do you think needs to worry about the instruction set, or what tool needs to worry about the instruction set?
Compiler.
The compiler. What else do you think is important about the microcontroller?
The architecture.
Say it again.
The architecture.
Error detection.
Architecture.
Did you say architecture or error detection? Which one?
Architecture.
Oh, architecture. Ah. Who do you think worries about this? By the way, I'm going to add something to this. What else for the architecture? Hint.
The developer, compiler, and user.
Compiler, debugger,
And the developer.
and the what?
Developer. The guy who writes the code.
Does it really matter? We'll say the tool. We won't count a person as a tool yet. What else do you need to know about the microcontroller? All right, how much memory? So what do you think what worries about that?
Linker.
All right, the linker. Because the linker needs to know where to download what you create, right? What else do you think it matters? What tool? Speak up.
Is that the downloader?
The downloader? It needs to know where to download or what address to download that certain code to, right? Where's the start of Flash? What else?
Compiler
Compiler.
and debugger.
Compiler, debugger. And? Oh, I already did linker. Is there anything else? No, that's about it. Keep in mind that the memory and the memory map will tell us how much RAM you have, how much flash you have, and where it exists on your machine or on your little chip. Because then it will be able to say, okay, the flash goes starting at this memory location, and the RAM, your volatile memory, will start over here, and that's where I put my variables. And by the way, does anybody off the top of their head know what's the beginning address for RAM? Okay, good. I mean, that's the point. Good. You don't know, right? Should you know?
Depends on the OS.
Yeah, depends, but for most people, it doesn't really matter, does it? Now, do the tools need to know where it starts? Oh, yeah. The tools need to know where you're going to start memory, where you're going to start RAM. So the nice aspect of that is that now somebody else who works for Renaissance or some company like that is actually going to help you identify where RAM starts for that particular chip. And they'll automatically put that into the project that you create that says, oh, you've got that chip, that specific application of that chip. Well, it has 512 bytes of flash, and it has 96 bytes of RAM, and it starts at that particular address. And so the nice aspect of that is that the tools do that for you. That's one of the joys of an integrated development environment. That's why it is your friend. All right. Hey, this is a neat board. Can I keep it? No, I'll give it back to you. So what else do you need to know about your embedded system? Well, I guess I can pull this out, right? And you said that, say that louder?
Peripherals.
Peripherals. So, oh, by the way, this is, I'll put that under here, peripherals. So who needs to know about that? Which tool? Again, all of the above. Why? Well, do you know what the address for port 4 is in the memory map? Now, could you find it if you were given some lists and stuff? Yeah, probably. All right. Is it important for you to know? Maybe. So the nice thing is that the tools will help you do that. Question?
The address for the ports and stuff are defined manually, right? Or is it? Does it come with the any of the ID components?
Ah, good question. Who actually identifies where all these ports are, right? And the answer to that question is that's actually manufactured into the chip. It's hard-coded into the chip. How does the developer know that? That's actually, I've got something that I'm going to show in a couple of minutes that tell you where that is. All right, good question. That deserves a trip to the prize closet. Have you been there yet? No. Oh, good. You get a trip to the prize closet, unless you want one of these things I have in the bag, so in the box. So, again, let's step up. What do you need to know about your embedded system? So let's, again, look at this entire board. What else do you think you need to know?
Communication protocol.
All right. Communications protocols, or maybe libraries, tools, existing code, right? Because, hey, what do we have right here? Right there. An LCD, right? Has anybody here actually written the device drivers, in other words, the code that goes all the way down and determines which ports to wiggle for the LCD? You've done that on this board?
LCD.
Phew. I gotta have you come down and teach the course, right? No. None of you have really done that, right? That's already been provided for you. So that's some of the devices, or I'm sorry, that's some of the information that's provided for you by the integration development environment, and also by some of the include files, all right? So now I'm talking about include files. What do you think that also identifies? Some could be a definition, a mapping of hardware I/O devices to ports. So, for example, we have on here an RS-232 port with an RS-232 chip with a little wire that's probably running over here to the microcontroller. that goes into one of the ports in the microcontroller. Does anybody know which port that is? No. Why do you not know what it is? Because somebody has already done that for you. Somebody has created a .h file, an include file, that identifies for you, all right, all we have to do is say RS-232 port 1, and it knows that that's tied to a specific pin on the board, and it's going to go out to your RS-232 port 1 that you can plug into your PC, for example. So that's one of the advantages. Rather than have you go really far down in the details of this, we've kind of raised you up a little bit and given you the tools to understand how to do it. So we've taken you a little bit higher than having to actually wiggle little bits as they go in and out of the board. We will look at how to wiggle in and out of the board later, but I just thought we would, have you do the high level stuff first and then learn a little bit later down. Everything down lower. All right? So, just to recap something that we have discussed earlier, we did have a concept where and this was discussed in an earlier class associated with C. We have the typical, you start with C source header files, it goes through a preprocessor, a compiler, you link in, and then you create an executable image. What tool handles that executable image and does something with it? Which of these tools?
Downloader.
The downloader. So it knows where it should be loaded to, and actually, unbeknownst to you, inside here, right there, is another microcontroller that is running on your board. You don't program that microcontroller. It actually sits there and communicates with your regular microcontroller. This is called it's not so much a ROM emulator as it is a debugging circuit. And in fact, there it is. It says the Seeger J-Link debugger. And so it is a chip. Actually, it's a Renaissance chip as well that is communicating via USB with the PC. So what you really have going on inside of your system is you have your PC with your tools running, and via USB it is communicating with an H8 debugger, H8 chip, which is your debugger, and this in turn is communicating with your Renaissance RX62N chip. And then the RX62N chip has all of these peripherals that it's communicating with. So what you're doing is you're sending code when you download. You send code from the PC to the chip, and it is actually relaying and putting it directly into certain parts of here. But the interesting thing is that this has code written by Renaissance. It has already been written by them, and you don't have to worry about anything associated with it. All right, does that make sense? I think I have gone into enough detail about all of the features of Hue, and you've seen examples, so I don't really need to go into how you start a project, because I think you could use Chapter 4 to help you identify everything that is associated with it. You should have enough background in the C language to know that if you want to use certain functions, like if you want to use string operations, you need to use certain H files. If you want to work with math, trigonometric functions and all, then you need to use the include file called math.h. All of these are listed in your book, and I don't really need to go into great detail about that. And by the way, you should be reading the book because there's some good information on there that will help you do your labs as well. There are a couple other minor things I do want to cover, and that is associated with where things exist in your memory map. Now, as you remember, you have seen the memory map before. If you remember, the memory map was associated with our board here. There was some on-chip RAM that went from 0 to 0001 7FFF. So, what I would like you to do is to tell me, according to this memory map, how much RAM is there in that first area. So, do that conversion. I know a lot of you have calculators, right? All right, does anybody have an answer for me? All right, your answer is how much? So those of you, let's check on this. X 18000. We'll change it to decimal, and it's 98,304. By the way, if you divide by 1024, that's a K. 96K. 96K bytes. Now, here's the other interesting thing to assess from all of this. Where are our I/O devices located? In other words, the addresses. Where are they?
Peripheral I/O registers.
All right. It's where it says what? Peripheral I/O registers. By the way, I also see that there's another thing here called peripheral I/O registers, and some more called peripheral I/O registers. So maybe we should look at this in a little bit more detail. That's a future class. All right? Now, where is everything located? I mean, when you say peripheral I/O registers, that implies that this has a memory address, right? So, as a part of the tool, you have an example right here of some memory addresses. So, hey, look, oh, stop. All right, did that work? Oops, wrong way. So, here we go. Port 1, or port 0, has the memory address of 8C000. Is that within our peripheral address range? What was our peripheral address range? That was 80000. So that fits in there, right? And in fact, take a look. Here's port 1, port 2, port 3, blah, 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 all the way down to port G. Oops, I'm doing that and you can't even see that. Here we go. So that tells me that the ports come one right after the other. Didn't we say that there was also another aspect? There were direction registers and things like that. So it looks like the control registers aren't next to, or they don't have the address right near these others. By the way, are these going up by a? Are they going up by a byte or by a word? They go up by byte, right? Because we go from C000 to 80 or 8C to 8C001. So obviously each of these is incrementing by a byte address. So that tells me that each one of these ports is a byte. Now if you go a little bit further, volatile. Volatile means what? It explodes when it hits air, right? We'll look at what a volatile variable means later. And it's a structure, ST port A, that gives a definition of something in our structure that's in another part of this file. But this is, I just cut this from one of our files that actually says these are what the addresses are for our ports. So it's already working. All you have to do is say port 5, and your compiler and all your tools will know that it is specifically memory address 8C005. And that's the joy of an integrated development environment, because it will do all the work for you. Or at least all the lower level work for you that's not as much fun. All right, so with that in mind, I believe I have covered, and I've covered everything that I want to in this chapter. Thank you very much.